Okay, so we'll continue on with the cyclic conformational analysis with chair cyclohexanes. We'll do some more drawings, converting the flat structure into a chair. And then we're going to transition into stereochemistry, which will be our next couple lectures before your exam in this module. So I think most of all the stereochemistry part is definitely where you want to start breaking out your model kits to understand that concept, because it ties back into a lot of what we've done so far with carbon and hydrogen uniqueness. And then there's a tricky part about stereochemistry that really the model kits will help you visualize that concept a lot better. And that deals with the underlying thing of symmetry. So we'll continue on with these di-substituted cyclohexanes, where the issue was in the flat structure where things are presented as a wedge or a dash. How do you convert it into a chair drawing and figure out if things are axial or equatorial? So I believe we went through the 1-2. I don't think we got to the 1-3 yet, so we'll do that, and then the 1-4. So we'll convert these names to the flat structure. So we have cis. I'm going to draw these as bolded wedges. So one ethyl. And at the 3 position, we have a methyl. So in the flat representation, I've drawn both of those groups sort of out towards you, or another way of saying that is up. So we'll just draw a cyclohexane. And to keep consistent with the prior lecture, I'll put this carbon here as 1, that's 2, and then that's 3. One thing I do want to point out, because I don't think I emphasized it last time, in the chair cyclohexane, remember we had those, the top and the bottom faces. So see these carbons here, this one, and that one. See how they're like up? And then this one, and that one are down. That can help you translate the flat into the chair when you're putting these substituents in. So I've labeled carbon 1 right here. That carbon is pointed down. So when we're kind of looking at the edge of the ring, we want the substituent, the ethyl substituent, to be up. So we know that for every carbon there's an equatorial and an axial bond. So for that ethyl group to be up, it has to be equatorial here. And because it's on the right side of the molecule, it has to point to the right. So that's the equatorial bond. It's up. And then we add the rest of it. Now it's an ethyl group. Positionally, we want a 1-3 relationship, so 1, 2, 3. That carbon is also down. So to have the methyl group up, it needs to be equatorial. That way they're on the same face. So overall, for that relationship of 1, 3, both substituents are equatorial. If we do a chair flip, and to make interpreting this easier, the carbons that I'm going to flip are going to be that one that's down and that one that's up. So that's the flip. Now, what can be a little confusing about this is the numbering on the ring looks a little different. So this becomes carbon 1, that's 2, and then that's 3. And we know that when we do a chair flip, equatorial goes to axial and axial goes to equatorial. So now we're just going to make those things axial. So this is 1, 3, axial, axial. Notice in both drawings, those substituents are still pointed up. The preferred conformation would be the one that's di-equatorial. Any questions? Yeah.
How do we know which carbon is the first carbon on the chair diagram?
So I guess my interpretation of that question is, how did I number this? You can number this chair any way you want. You're still going to get the same result. Really, the difference when you do that is just kind of how your eye is looking at that ring. So that's one thing that you can practice. So for example, if I said this was 1, then 2, then 3, so carbon 1 is up. So the up bond here is axial. Then carbon 3 is up, so that up bond is also axial. So I've in that perspective, I've drawn the diaxial conformer. And when that ring flips, we would now get the di-equatorial. So you end up with the same structures, it's just your frame of reference, depending on how you number it, changes. So for the trans, I'm going to keep that one carbon as kind of the up substituent, then I'll make the 3 methyl group down. So now they're on different faces, so that's trans. And then we can use the prior example, because that one position we kept the same. We know that that's got to be equatorial. And then because the 3 position is now down, on this down carbon, the bond is axial. So we have 1 equatorial, 1 axial. Which means that when we flip it, we're going to end up with the same thing. One's going to be axial, one's going to be equatorial. So overall, there's not really, I would say, a winning conformer in terms of stability. You know, the difference between ethyl and methyl in terms of the size isn't too great. So these conformers would be more equal in their population. Any questions on the 1,3? So you would do the same sort of analysis if you have, you know, 2 or more substituents on the ring. For any sort of flat cyclohexane, you can still draw the 2 chairs through the ring flips and just figure out whether the substituents are axial or equatorial. So now we'll do the 1,4. So we'll start with the cis. So 1 ethyl, 4 methyl. And I'll use that numbering. So the carbon 1, that carbon is down. We want the ethyl group to be up, so it's going to be in an equatorial position. So we count over to 4. The 4 carbon is now up. We want the methyl group to be up, so the up bond there is axial. So we have equatorial, axial. And then so when we flip it, we're going to end up with an axial equatorial now. So that's another situation where there's not really going to be one conformer preferred over the other because you have a mix of them. So now we'll do the 1,4 trans. We're going to keep the ethyl group up, and now the methyl group is going to be down. So carbon 4, because that carbon is up, to make the bond that's pointed down, in this case, is going to be equatorial. So we have now 2 equatorials. So when we flip, they're both going to be axial. So the diequatorial one would be the predominant conformer for that pair. So just to review why that is, if I put in the other axial hydrogens. That has these 1,3 diaxial interactions, which is kind of a space thing, and that's strain. And then you also have it on the bottom face with the methyl group as well. So steric, the way that I interpret that word, it just means space, because from hydrogen up to any functional group, remember that there's the nucleus, the electrons. Even though those are particles, they have these van der Waals radii that take up space. As you get increasingly larger, things can't occupy the same space at the same time, so they repel against one another. So, yeah, you should be able to take the flat version and figure out which chair it corresponds to. But then if you think of it the other way, if you're given a chair, can you identify the kind of up-down relationships and then be able to draw the wedges or the dashes?
So ultimately, we'll be given either or to begin with.
Yes. Any questions on the 1,4? So here is a kind of summary of all that, where there's the three positional relationships, so 1, 2, 1, 3, 1, 4. And then really what I've drawn is just kind of a bond. And you can imagine whatever substituent there bonded to those things. So of the positional relationships, they can be cis, which is the same, or trans, which is opposite. And then the summary of the two different chair conformations. So when you look through all those possibilities, like in this one, see how the arrows are different? That means at equilibrium that the diequatorial would be the preferred one. When they're equal, that means they're kind of the same in terms of one substituent's axial, one's equatorial. But each of the three different relationships does have one that is preferred. So in this case, the trans, that cis, and then this trans one. Questions? Again, your model kits will help if you have trouble either converting from the flat to the chair or doing those flips. They'll help you figure out where things end up. When you do the chair flips, though, you want to make sure that you're doing a proper chair flip, in that, in your left hand, you have one carbon, and then your right hand 4 carbons away, so that you do that flip correctly. So let's kind of put all this together, so to answer the prior question, if we had this chair and we wanted to draw it flat, that would be the flat cyclohexane. So when I look at the two main substituents, I have a tert-butyl group and then a methyl group. They're both pointed up. So that means they're cis, and then I would use these bolded wedges to represent that. So the question asks, what is the relationship between HB and HD? What is it? So they're anti. So if we classify both of them, HB is axial, HD is axial. So it's a transdiaxial relationship, meaning that their dihedral angle is 180 degrees. So what would be another way of doing that if we were to make a Newman projection looking down that bond? So imagine that your eyeball is kind of your left eyeball is here and your right eyeball is there. Then we can make that kind of double barrel Newman projection. Put the substituents in, and then it's a little bit easier to see the dihedral angle. So we'll start with our left eye here, looking down that sigma bond, which means HB has to be up. Then HC is going to go over here to the left. Then the other substituent is that carbon right there bearing the tert-butyl group. I'm not going to draw that in right now because I want to put in kind of the right side carbon. So from that bond, we need to go back up. And so now that's making this carbon right here. So really what we're doing is making two Newman projections at once. So I'll put in the back carbons for each. So on this back carbon, HD is pointed down. Which means HE is up and to the left. You see how HC and HE, they're kind of both on the left side of that molecule, and so that's what we've represented here. So then we have the third substituent, that's going up to the methyl group. And then everything else is, the H is on the other side. So there you're able to see as you move from HB to HD, you have to go 180 degrees for the dihedral angle, and that's anti. Yeah.
How would you know which angle you're looking at it from?
You can start from either one of these. So as we start from HB, we need to look along because we're looking along the carbon-carbon sigma bond axis in the Newman projection. So as we rotate, where do we stop when we get to that desired H, which is HD? So from here to here, that's 180 degrees. So if we wanted to analyze these other ones, we would, kind of how much tilt to get to HE or to HC. So this one says HC to HE. So these are di-equatorial. So what do you think their relationship would be? So they have to be gauche. Remember, that's 60 degrees. We know they're not anti, because that is 180 degrees. Maybe they're best friends, maybe not. We know they're not eclipsed because we can say HE is up, HC is down. If they were eclipsed, the dihedral angle would be 0. So that, again, is another way of looking at it where HE, again, is up, HC is down. So through the di-equatorial, they're in a gauche relationship. Questions on that one? So this is a little, I guess, different phrasing, more about the angle. So HA to HC. So HA is axial, HC is equatorial. So what would their angle have to be? So it would have to be 60. So again, it's gauche. Or GAU, however you spell it. So things that are transdiaxial are always going to be anti or 180. I think that is going to wrap up the cyclic stuff here. one more brief slide. I put this in here because every book has this. If you take two cyclohexanes and bridge them together, so we learned about these bicyclo compounds. The unsubstituted just carbon rings, this is called decalin. So you have cis and trans decalin, and that relates to the bridge junction. Only the cis decalin can undergo a ring flip. So if you kind of think of it as, can't really cover it up, but maybe I'll draw it. So think of it as like a 1-2 relationship of like cis 1,2 dimethyl, but now that you've constrained that into a ring, the cis one is the only one that can flip, where you have axial equatorial going to axial in blue, equatorial in red. The trans ring junction, the bicyclic one, will not allow that flip to happen unless you kind of break this bond first, which isn't going to happen under normal circumstances. And the decalin relates back to the steroid nucleus that we saw that had those 4 rings. So typically in a steroid, you have kind of a decalin substructure and then some other stuff coming off. So steroids with the cis ring juncture there can flip, and the reason that's important is because a lot of steroids, their biological function is related to their conformation. Questions? So I'm going to introduce a little bit of nomenclature in terms of halogens. So we've learned about alkane nomenclature. Now we're going to start putting halogens on the carbon backbone for the purpose of learning a new type of isomer. And so when you have a halogen, basically you're using, you're dropping the I-N-E and then using O to name it as a substituent. And I want to introduce the exercise by looking at some molecular formulas. So we'll start with a 3 and a 4 carbon count where we've substituted an H for some halogen. And to make this a little more streamlined, both of these formulas have no degrees of unsaturation. So we're going to convert the molecular formulas into constitutional isomers. So for C3H7 Br, 0 degrees of unsaturation, how many constitutional isomers can you draw? So remember, C3 is propane. And so along that 3-carbon backbone, we have to substitute H for bromine. And if we do it in a logical manner, there's 2 spots we can do it at, positions 1 or 2. And so that would be called 1-bromo-propane. Then the other isomer would be at the 2 position. And that would be 2-bromopropane. They would have different melting points, different boiling points. You can go through the CH uniqueness. You'll find that they'll be different as well. So that those 2 isomers are reasonably differentiated through physical and spectroscopic properties. So here we end up with 2. So let's move up to now C4, and then to add a little flavor, we'll just use chlorine now as the halogen. So with C4, we have the linear chain butane. From that, we can put the chlorine either at the 1 or the 2 position. So that would make 1-chlorobutane. Or if we put it at 2, that would be 2-chlorobutane. In terms of constitutional isomers, remember we have the linear chain, and then when we're at a carbon 4 count, that's when we can have branching. So we can have these propane derivatives where now we have to put back in a carbon and now the halogen. The carbon has to go at position 2. So that's our kind of skeleton now to put back in the chlorine. And the chlorine can go either at the 1 or the 2 position, so we can get 2 more isomers. So 1-chloro, 2-methyl propane. The other one would be 2-chloro, 2-methyl propane. So based on that exercise and the responses, we would say we could draw 4. So 4 constitutional isomers, but that's not the total number of isomers possible. So here's a recap of that with the molecular formulas, the parent carbon chain, and then as you do the substitutions of the halogen at the different positions. So when you're doing this type of problem, it's always helpful to number the carbon backbone. So when you put in substituents, you can name it and then not kind of duplicate any answers. So the issue is with C4H9Cl, are there only 4 isomers? And the answer is no, because of this one right here. The issue with this one is this bond. So remember that carbon always forms 4 bonds. And we've seen so far for a tetrahedral or sp3 hybridized carbon, we were using these wedges and dashes to show if something's coming out towards you or going away from you. So if I draw in, that implicit hydrogen, that carbon now has 4 different things bonded to it. A methyl group, an ethyl group, a chlorine, and an H. So this bond can actually then translate into 2 different molecules based on the arrangement of the H in the Cl. Because we're going to leave the carbon backbone in the plane of the board. So this relates to symmetry. So there's a lot of different elements of symmetry. Probably the most common one is a mirror plane. So for example, I would say for the most part, I have one element of symmetry, and that is kind of like slicing me right in half. So if I look at my hands here, my hands are mirror images of one another. So if you move back from that and slice me in half, my left and right sides mirror one another. So the mirror plane is kind of orthogonal to this axis. If I chop myself this way, that's not a mirror plane. So that's 1, 2, and then the third one would be this way, right? So that's not a mirror plane as well. If you're pre-professional going into like med school or vet school, they have different names for these planes. Does anyone know them? These axes. What? So dorsal. Yeah, I think that sounds familiar. Like I think sagittal is one or something like that. So why is that important? Like if you're imaging the human body in like an MRI, those are the terms that are thrown around to orient, other doctors and the patients about where exactly something is wrong. And so that kind of translates into this for imaging a molecule. So when we look at these 4 constitutional isomers, why is that one special? For the 1-chlorobutane, if you look at every carbon on the chain here, they have at least 2 of the same substituent. So here, hydrogen, 2 hydrogens, 2 hydrogens, 2 hydrogens, 3 hydrogens. The same thing for this, 2 hydrogens. Now that carbon has 2 of the same groups, methyl. And then this one has 3 of the same. So that is the unique carbon where all 4 substituents are different. You have methyl, ethyl, H, and Cl. You have a question?
No, it's a Carol Center.
Yeah. So how do we depict that? So there's a couple different terms thrown around. I've forgotten the explicit definitions of each, but either chiral center or stereogenic center. So this won't mean much to you all, but like, you know, back in the day when like hi-fi audio, like now in stereo. So that means kind of 3 dimensions. So the asterisk is telling you that that carbon has 4 substituents. And so there's 2 ways of representing that. So we know that the carbon's sp3 hybridized. That means it's tetrahedral. You have a bond coming out and a bond going back. And so we can put a chlorine coming out, an H going back, or we can reverse it. Chlorine going back, H coming out. So name-wise, they're both called 2-chlorobutane. But, you know, say someday, you know, you have children who are identical twins, you wouldn't call them both Steve. You have to call them different things because they're different people. And so we have to do the same thing with these molecules because they are different, even though they have the same sort of parent name. So we have to look at that carbon, then assign priorities to the atoms bonded to it, and that's going to give us a way to differentiate those molecules. So these are called stereoisomers, and more specifically, they're mirror images of one another. And the term that's used is called enantiomers. So every one stereo center can generate 2 enantiomers. So as we proceed through this, it's kind of straightforward in a way, but then we end up with these molecules that have a little bit of weirdness to them due to these other symmetry elements present. And so there's going to be a lot of terms that we start using under the concept of stereochemistry. So how do we name these things? So I'm going to use the yellow for hydrogen here in this example. The central carbon here, as you can see, there's 4 different colors bonded to it. But I want to keep yellow as hydrogen, and then the red, green, and blue are just 3 other different things. So in one sense, so hold the white in my left hand, the blue, so I'm going to do that. Make sure that when the carbon bond is up, so if I do that, I'm saying the red one is up. Now if I do it this way, now the green one is up. So once you, again, use your model kits and orient them, you'll see that they're mirror images of one another. So what that means is You can always align two of them. So like I'm just going to rotate and make the yellows line up and the blues line up. So the yellows are kind of overlapping now in blue, but you'll see that these are now different. So the model kits will help you, when you're looking at these things from different perspectives. And as you do more of that, you'll be able to do these flips and rotations and inversions in your mind. So say, for example, we assign, we're going to keep this just a carbon. The yellow one's H, and then the colors will have just different halogen meanings to them. So this one is that. This one is on the left here. So we have blue is fluorine, green is chlorine, and then the red is bromine. And so that makes the carbon with 4 substituents. So the real question is, they're going to have the same sort of parent name, but they are different molecules, so they need to be designated that way. And the way that we do that is through this addendum to the nomenclature rules. It's usually just abbreviated CIP or CIP, so Kahn, Ingold, and Prelog. These were the 3 scientists that came up with these rules. Really based on stuff from the periodic table that is logically coherent. So there's no way you can mess this up once you understand the rules of this. So if I highlight the stereogenic carbon in red here, we have H, F, Cl, Br. So 4 different substituents. Of each of those atoms, you're going to assign a priority based on the atomic number. And so that's what the number you see here is from the periodic table. So notice in both cases, 9, 17, 35, 9, 17, 35. Those numbers are the same, but there's something different about how you view the order of those numbers. So again, just to recap, a carbon with 4 different substituents is a chirality or stereogenic carbon. You go out to the immediately bonded atom. You don't go out more than 1. What is that element? Find its atomic number. So that's the first thing you're going to do. And then from that, you're going to assign a priority. So the higher the atomic number, the greater the priority. So for this one, I have the H in the fluorine in the plane. The bromine is coming out towards you. The chlorine's going away. So this is the left molecule. For these rules to work, what you have to do now, I'm holding the lowest priority group, the hydrogen, because that was atomic number 1. You have to point it away from it. So now you're looking at 3 substituents. So really this is like a Newman projection where you're looking down a carbon H for carbon something bond. And so there's your atomic numbers, and then as you see the priority 1, 2, 3, 4. Since hydrogen's the lowest priority, it goes away from you. And then everything else is just descending atomic number. So bromine gets priority 1, fluorine 2, fluorine 3. So 1, 2, 3. When we do that like circle, that's clockwise. So the designation for that is R. So this one's R because we were going clockwise, and then this is the other one. Notice the priority groups now. So we're going 1, 2, 3. We're going counterclockwise. That's called S. So any stereogenic center will have either an R or an S designation. So nomenclature-wise, that's how you differentiate them. The thing you don't want to get tripped up on as you look at more complex molecules, whatever carbon atom you're determining R or S from, it's just the immediate 4 atoms bonded to it. Don't start walking off, three atoms away, because that's not how it's done. So the question was, what if you have like a methyl and then an ethyl and maybe some other. So let me kind of walk you through the logic of this. What's the issue here? So there's the stereogenic carbon. We have methyl, a propyl, and an ethyl, so 3 different substituents. But when we walk out, we see carbon, carbon, and carbon. So the atomic number of carbon is 6. You can't make a differentiation there. So at that point, then you look at the stuff bonded to it. And so in green, what I'll do, so down here, you have 3 hydrogens. So we could say for those 3 hydrogens, it's 1, 1, and 1. For the ethyl group, we have a 6, a 1, and a 1. Because I'm looking at the 3 things bonded to that, 2 hydrogens and 1 carbon. So for this one, that would be 6, 1, and 1. Of those 3 that were the same originally, you've relegated that to a lower priority, but now you still have this, which is the same. So then you can go out 1 more, and you'll see that we have 1, 1, and 1. then you have 6, 1, and 1. So you kind of, at that point, you do move along the chain if things are equivalent. So if we kind of finish this off, I know it's getting crazy with numbers here, but this would be priority 1. That would be 2. This would be 3. So the lowest is going away from us, so that would be S. And then that has to be R. Any lefties in the crowd? I mean, handedness, not political views. So a couple, 3, 4. Do you know what this S stands for? Sinister. Why do you think it stands for that? So in the majority of people are right-handed, right? So when you encounter a left-handed person, you're like, there's something sinister about them. So that's where the S comes from in that nomenclature. So now the issue is, we have these 2 compounds with the exact same molecular formula. We were able to differentiate them according to this nomenclature rule. That is a human construct, the CIP nomenclature algorithm. But if you look at the physical and spectroscopic properties for both the R and the S enantiomer, they're exactly the same. Melting points are the same, the boiling points, the masses, the chemical shifts. So other than us drawing them on paper, how do we actually know that in reality these 2 things exist if all of this stuff is the same for both of them? So you've probably already done this in lab. The technique that differentiates them is called polarimetry. So you did that in lab, I think, already. So I want to be, just hammer this home. That the R and the S, that's a human rule. The molecules aren't floating around in space and time with like a letter R and S associated with them. The way they're differentiated is with the sign of the optical rotation as measured from polarimetry. So the sign is either going to be negative or positive based on how the sample rotates light. That's a measured piece of data. It always has to be measured. The designation of R or S has nothing to do with what that sign is. Meaning that for every R enantiomer, it's not automatically negative, or it's not automatically positive. It just has to be measured. So what I can say now, before introducing the optical rotation stuff, for this compound, the R enantiomer does have the negative rotation. The S enantiomer therefore has to be positive. whatever that value is, they're the same magnitude. So say it was, the optical rotation was like 56. The R would be negative 56, and the S would be positive 56. The sign is what changes. The magnitude is the same. So why does polarimetry differentiate, these stereoisomers and things like IR and NMR don't? So polarimetry operates using light. So we talked about, the electromagnetic spectrum in these different regions. Light has 2 vector fields to it. So there's an electric field and a magnetic field. And so from that kind of red direction to this teal direction, that's 90 degrees. So those 2 vectors are orthogonal. And the kind of white light that you see, coming from the fluorescent tubes, it's a lot of different wavelengths. And so what the polarimeter does, it selects out one of those wavelengths. And so in doing that, it's polarizing a certain wavelength, which then allows you to select amongst these electric and magnetic fields. So if you were able to kind of visualize, the electric and magnetic vectors, they would kind of be infinity amongst this circle. You could put a polarizing filter in there that's going to select out one of them. So when you go outside in the summer and you put on sunglasses, this is essentially what's happening. You're filtering out a lot of that light. So you filter out a light, it runs through a sample, and that light is going to tilt either to the left or to the right, clockwise or counterclockwise. So things that go to the right get the plus sign. That's called dextrorotatory. And it's given another symbol just like this sort of small cursive D. Things that go to the left are levorotatory, and they get the minus sign. So the experiment that you did, there's a light source, there's a polarizing filter, then you have a tube with your sample in it. So you have all these EM vectors. One of those is selected out through that filter. And then as you can see that up-down arrow, when it moves through here, you see how it starts to tilt? And that at the other end is this kind of dial or analyzer where you can measure the magnitude and direction of which that light tilted based on its interaction with that sample inside. So you get some data, you throw it into an equation, and then for the compound itself, it's called the specific rotation because it's normalized under the conditions. So the specific rotation has the sign plus or minus, and then however much that light moved around, the circle. That value will be opposite sign, but equal magnitude for the enantiomers. So if you have a sample that is a 1-to-1 mixture of R and S, the specific rotation is going to be 0, because anything that goes to the left is canceled out by what goes to the right. And that's called a racemic mixture. So at this point, what do we know? You can have a pure R enantiomer, a pure S. And then you have this 1-to-1 mixture. So at 1-to-1, the specific rotation is 0. From that center point, moving either to the R or to the S, you get an excess of one of those enantiomers. That's going to reach the maximum for the pure enantiomer, whatever that value is. The specific rotation equation is shown here. All it really does is normalize the optical rotation you observe to whatever concentration you made your sample times the path length. So experimentally, to make this easy, typically that you want the concentration to be 1 gram per milliliter. The path length is usually 1 decimeter or 10 centimeters. So that makes the denominator here pretty straightforward. And then what falls out of that as it's calibrated to whatever the temperature is and the wavelength is the specific rotation of the sample. So if the light tilts clockwise, it gets the plus sign. It's called dextrorotatory and given that small d abbreviation. If it goes the opposite way, it's negative. That's levorotatory or L. And I need to stress this. There's no correlation between what you figure out as R or S and what you measure. So that has to be measured for each compound. Then you can go back and fill out the complete name. So we're about out of time, but what we're going to carry on with is outside of those three scenarios, pure R, pure S, and the 1-to-1 mixture, what about everything in between? The excess of one enantiomer over another.